Welcome back to the fifth section of Chapter 1. Here we're going to be looking at the properties of exponents. These are ones where they're very, very similar to each other. There's going to be a lot of names. The nice thing about these properties is that you need to know the property and how it works way more than remembering what the actual name of the property is called. So we have a couple learning targets. 1, I can simplify expressions involving exponents. And 2, I can use scientific notation. So first of all, some basics for exponents. We'll have things look like this. A to the x, that's how you'd say it. This a is what's called the base, and the x is what's called the exponent. In exponents, parentheses matter. Negative 2x cubed, negative 2x cubed, and negative 2x cubed all mean different things. So the placement of these parentheses is important. So when you get a problem like that, you need to be aware. This first one, if we expanded it out, x cubed means x times x times x. So this would be negative 2 times x times x times x. The second one, it's the 2x that's being cubed. So that'll be negative, then 2x times 2x times 2x, which we'd multiply the 2's to get that negative 8x cubed. This one, the negative is included in as well. It's negative 2x times negative 2x times negative 2x, which in this case is negative 8x cubed, which this one and this one, the two bottom ones, happen to be the same in this case, but if this exponent was even, this one would still be negative, and this one would be positive. So the placement there does matter, and how you deal with them with the placement does make a difference. So something to be careful with. I know a few people miss this on the pretest. So now getting into properties of exponents. The first one we're going to look at is called the zero exponent property. If we have something to the zero, what does that equal? You might remember, oh, anything to the zero equals 1. And that is true. But why is that? We can actually see this with a really quick pattern. If we start out with just a cubed, a squared, and a to the first power, we can expand these. A to the 1 is a squared is a times a cubed is a times a times a. Each time we just multiply by another a. Well, now what if we were coming at the top, starting at the top and working our way down? To get from a times a times a to just a times a, we would divide by a. And we divide by a. And then we divide by a. What is anything divided by itself? 1. We can keep going. We can divide by a again. A to the negative 1 is 1 divided by a. A to the negative 2, we divide by a again. That'll be 1 over a times a, or 1 over a squared. We can do the same thing for negative 3. It's 1 over a cubed. And that gets us to our second property, the negative exponent property. If we have a negative exponent, what does that mean? It means we have 1 over a to the n. So it just flips it to the bottom of the fraction bar. If it's already on the bottom, it would move it to the top. With a fraction, it just means reciprocal. It's the reciprocal. So 2/3 to the negative 1 is 3/2. So that's what the negative means. When it's telling you to simplify expressions, most of the time we don't want negative exponents. So you'd have to move whatever that is to the bottom of the fraction bar. So if you had a to the negative 2, that's actually, it'll be over a squared. Something's over a squared. If it's just a to the negative 2, it'd be 1's over a squared. So these are two of our properties. We have a bunch more though. And I wore out the P button on my keyboard writing these, because we have product of powers property. That would be if we have two things with the same base multiplied together, what do we do with the exponents? So a to the m times a to the n. And notice it's a to the power, a to the power. These two things have to be the same. For pretty much any of these, those two things are the same. Otherwise, these don't work. So a to the m times a to the n. Well, this is m a's all multiplied together, and then n a's all multiplied together. Does this multiplication sign mean any different than any of the other multiplications? No. So we have m of them, and we have n of them. We just add them together. A to the m plus n. So if we have x cubed times x squared, we would end up with x to the 3 plus 2, which is x to the 5. Same thing with quotient of powers property, except instead of multiplying, we're going to be dividing. If when we multiply we add, what do you think we're going to do when we divide? Subtract. It'll be a to the m minus n. If you were to expand these out, you'd have a whole bunch of a's on top, a whole bunch of a's on the bottom. Then you'd be able to cancel out the a's because it's multiplication common factors. Next one's power of powers property. We had product of powers, now power of powers. And again, I wore out the P button, I'm telling you. So the power of powers is if you have a power of a power, a to the m to the n. Well, this would be a to the m times a to the m times a to the m times a to the m n times. So it's really just multiplication. We know when we multiply, we add. So we're going to have to add m n different times. What's a shortcut for repeated addition? Multiplication. When we have power of a power, we multiply the exponents. So this will be a to the m times n. So when we multiply, we add the exponents. When we have a power of a power, we multiply the exponents. So we've had product of powers, quotient of powers, power of powers. Next comes power of a product. But we have that. That's, oh no, that one's product of powers. This is power of a product. What's different? Well, there's an a there. Other than that, it switches it around. We're going to have a times b to the m. So we have two things multiplied together with an exponent. Here we had two things with exponents multiplied together. So the quick description for this, distribute. The m distributes to both of them. If you want to think about expanding, you have a times b times a times b times a times b times a times b times a times b m times. Commutative property, you can rearrange the a's and b's, put all the a's together. You have m a's, that would be a to the m, and you have m b's, b to the m. But really just distribute. Make sure it goes to everything, including if there's a number in there. It has to distribute to a number. Then power of a quotient. Same idea except with a fraction. We have a fraction to a power. Distribute. A to the m over b to the m. And then scientific notation. Scientific notation looks kind of like this. This is just an example of a scientifically notated number. It's 3.0152 times 10 to the 8th. We use scientific notation for really, really, really big numbers and really, really, really small numbers. A lot of times it's used in science class, hence scientific notation, because science class uses really, really big numbers, the distance between stars, and they also use really, really small numbers, the weight of an atom. And so scientific notation gets rid of all of those 0, 0, 0, 0, 0, 0, 0, 0, 0, and gets us down to just what numbers are actually important here. And so here, this 3 is going to be important. That's the biggest part of the number. Times 10 to the 8th. That means we're going to move the decimal point 8 places to the right, because this is going to be a big number. And if you actually multiply this out, times 10 to the 8th, you actually get that number. This is mathematically accurate. So what does scientific notation need to have? It needs to have one digit and then a decimal point. That one digit needs to be between 1 and 9. So it would be 1 point, 2 point, 3 point, 4 point, 5 point, 6 point, 7 point, 8 point, or 9 point. If you have 0 point something, you need to move your decimal place over. If you have 10 point something, you need to move your decimal place over. And then it has times 10 to the number. That's how many places you move your decimal point. A positive exponent means it's a really big number. A negative exponent means it's a really little number, like 0.00000 something. And so this, I said you move it 8 to the right, you get this big number. Here's one with a negative, 2.3 times 10 to the negative 5. We move the decimal point to the left. When you have these ones, if you have 0 point, this exponent tells you a number of zeros. You need 4 after the exponent, 1 before. If you just go point something, then you need 1 less than that, so it's only 4. We can multiply and we can divide with scientific notation. We tend not to add with scientific notation too much. It's not really set up for that. But multiplying and dividing it is. So if we have two scientific notation numbers here, 3.2 times 10 to the 5th times 4.1 times 10 to the negative 3, we really actually have 4 numbers being multiplied. Because is this multiplication and this one any different than this multiplication here in between these two? No, it's all multiplication. The first thing I would do, get rid of those x's. Turn them into parentheses. 3.2 times 10 to the 5th times 4.1 times 10 to the negative 3. Now we can rearrange them. Let's get the numbers together, and let's get the 10 to the powers together. So 3.2 times 4.1, then times 10 to the 5th, 10 to the negative 3. Why would I do that? Because we can do these. These have the same base, and they're being multiplied, which means we add the exponents. 5 times negative 3, or 5 plus negative 3, is 2. We're going to have 10 squared times whatever this is. 3.2 times 4.1 is 13.12 times 10 squared. We can rewrite that back into more scientific notation form. But is this scientific notation? No, we have 2 digits here. We need to move the decimal over, so it's 1.312. And if we move the decimal over, we need to change the exponent by 1. Ways of thinking about it, this times 10 to the 2 is a big number. Make it an even bigger one. So it needs to be 10 to the 3. You could expand this out. It's like, all right, so times 10 squared, so that's going to be 1,312. Well, you need to make it 1,312. If we went 10 to the 1, that would just be 1.312, and there wouldn't be scientific notation there. So again, multiply the beginning numbers together, and then add your exponents on your tens, and then change it back into scientific notation if it needs to be. Sometimes it stays scientific notation. Division, same basic idea. We're going to divide the numbers and then deal with the tens. When we're dividing, remember, we subtract the exponents. But 2.4 divided by 2 is 1.2. And then 10 to the 7th divided by 10 to the negative 3, we have to subtract. What is 7 minus negative 3? That's 7 plus 3, which is 10. So it's 1.2 times 10 to the 10th. And this is already scientific notation. We don't need to change it. And so it's done. So multiplying and dividing these numbers in scientific notation isn't too bad. Just make sure that you split up the tens from the front numbers. And that would be our exponent properties in scientific notation. Have fun with that, and I will see you later.